Sounds great. Then let's do this. We were sorry. Am I not doing this right? Hit share my screen. Share screen. Start. Um, sorry. I don't feel that's what I want to do. I just want you to share the freaking screen. Sorry. Hey, that's what it's supposed to look like. Hold on. Okay. We were doing the biot savart law, where we figured out a magnetic field due to a wire. It was a kind of nasty equation where I have this wire, and if I have a small chunk of this wire, ds, where my current is going that way, and some point out in space p, where r, whoa, that r got away from me, where r goes from my ds to my point in space, the magnetic field due to ds at that point of space was mu naught over 4 pi I. Wow, did not give myself the right amount. dB equals mu naught over 4 pi times I ds cross r hat over r squared. Okay. And then we said, well, I might want to know the magnetic field due to all the little bits of wire, not just one little bit of wire. And so we would integrate both sides, ending up with a much more sensible mu naught I over 4 pi integral of ds cross r hat over r squared. And then what we were going to do with this first is we were going to find the magnetic field from a long, straight, current carrying wire. From a long, straight, current carrying wire. Okay, so we're looking for an equation of the magnetic fields. And we expect to see things in it, like the current I, constants like mu naught and 4 pi. And also, we would like to see some distance from the wire to the point. So maybe in R, we're gonna talk about this, like what sort of distance we'd like to see. Okay, so fair warning, this is a pretty ugly problem, because it's not really the right choice for the problem given, and you'll see that as we go through this chapter. Okay, so let's draw our diagram first. I have this long straight wire. It extends out to infinity on both sides. Very nice and uniform. It's got some current I in it, and we can give ourselves a coordinate system just so we can communicate well. I'm going to choose a random point P there. And so I would like to know the magnetic field right there. Now, each little bit on this wire is actually generating a magnetic field, and it could contribute to that point P. And so we're just going to choose some random little chunk of wire. Remembering that we're really trying to fill out this equation. So yeah, so first we choose ds. So there's my ds. We point it in the same direction that the current is going. Okay, and then we look, so there's our ds. Next thing we need to know is r. Now r goes from whichever little chunk of wire we're talking about to our point. So that's r right there. Okay, so mu naught I over 4 pi integral ds cross r hat over r squared. And we're integrating over this entire wire. So let's see what we can do here. One thing we could do is we could calculate this cross product, ds cross r. Because it'll be the magnitude of ds, the magnitude of r hat, and the sine of the angle between them. Okay, so ds cross r hat. So the magnitude of ds, the magnitude of r hat. What is the magnitude of r hat? It's easier than that. Because r hat's a unit vector, right? 1, right. So when we take the magnitude of r hat, that's just 1. And then we take the sine of the angle between them. We're going to be really careful. I'm going to call it phi. We're going to be really careful about what angle we're talking about as we go through this. Where phi goes between ds and r hat. And so ds is going this way. And so that's phi right there. Now, the next thing. We did a cross product. A cross product takes 2 vectors and gives you back a vector. So we have to figure out a direction on this as well. And we're going to right-hand rule this, where the pointer goes in the direction of the first, that's ds. Next finger goes in the direction of the second, that's r hat. And then our thumb is going to point in the direction of the magnetic field. So, like in terms of x, y, and z, which way is ds? X? Yeah, positive x. Okay, so we have positive x, and then we have r, so like this. And then I see, at least, yeah, I see lots of thumbs pointing towards the back of the room. Probably be better like this. Okay, cool. So our magnetic field right there should be coming out of the board in the positive z direction. So our B field here is going to be in the positive z direction. Now Tuesday, we did some right-hand rules where we put our thumbs in the direction of the current and we curled our fingers around to talk about the direction of the magnetic field. Does that match what our thumb right-hand rule? Yeah, so I like that. So if you put your thumb that way, when you're on top of the wire, your fingers are coming out of the board, right? Okay, so that matches with what we were thinking. Okay, this looks pretty good. Let's put a plus Z on here. And rewrite our integral. There's going to be several steps, so just be patient here. So we have a sine phi ds over r squared. And I'm going to have like a z hat somewhere. I'm probably going to drop that z hat and bring it back at the end, but this is in the z hat direction. Okay, so right now I have like 3 different variables in my equation. I have a phi, I have a ds, and I have an r. Now my ds, we're going to go along this wire and add up all the chunks. As I go along the wire and add up the chunks, will my r change? Yeah, right? Because as I go like to the various chunks here, my r is going to look different. Okay, so one thing we're going to have to relate r to ds. Okay, what about the angle phi? As I go along here, phi is the angle between ds and r. Is it going to change? Yeah, okay, so we're also going to have to relate phi and ds. So let's start figuring this out. The way we're going to figure it out is I'm going to drop a line down to here, and we're going to start writing all these in terms of like x, y, and yeah, x and y. Where if that's 0, I could take any of these chunks and I could make a triangle, right? No matter which ds I chose, would this distance, the distance in the y direction, the perpendicular distance between the point and my wire, would that ever change? Excellent. So no matter what triangle I chose, that would stay the same. So that's a convenient thing to start with. Where that will be A, that will be R, that will be phi, and then this distance right here would be the x position. And this is going to come up because we're on the left side of the x equals 0. Right now we're at a negative x. Okay, looking better. So last thing, we've almost got it in terms that are a little easier to talk about. The last thing I want to talk about I want to talk about ds in terms of x, y, and z. Looking at my ds's in terms of x, y, and z, what direction are they in? X, yeah. So instead of ds, I'm just going to write down dx. Okay, so ds is going to become dx. Notice that we can write down E equals r sine of theta. I'm sorry, r sine of phi. Or we can rearrange that and say r equals a over sine of phi. And what I'm doing here is I'm trying to simplify everything down so they're in terms of one simple thing instead of a bunch of different things. Okay, so right now I have, let's take this, let's plug it in there, and let's see how that's going to look. And let's take this and let's plug it in there. Slowly but surely. U naught over 4 pi. So I have sine of phi dx over a over sine of phi squared. I wonder why I have a y hat. I think I have an issue with my, nah. I can ignore that y hat. That y hat's not supposed to be there. Okay, sorry, typo in the notes. Okay, so I got my dx. I put in a over sine phi and it's squared because my r is squared. I have a sine phi up there. This is looking a lot better. Let me square this out and let's see kind of what's left over. Mu naught I over 4 pi integrating sine of phi over a squared and really 1 over sine squared of phi. Did that make everyone happy with that? Okay. Looking at this, I'm totally going to make that a sine cubed of phi. Just give me a second there. That a, is that a constant or a variable? It would be a constant. So we can take the a outside. Excellent. And then the last thing, I have a dx and I have a phi. As I choose different dx's, so ds is really, does my angle change? Yeah, just like it did when I asked it 2 minutes ago, right? So we need to relate this dx and this angle. And we're going to do it through the same triangle, where we see if I want to relate phi and x, I could do it through a cosine or I could do it through a tangent, right? Now I'm going to choose tangent because that lets me use this a, which is a constant, instead of the r, which I would then have to change back into an a. So what I'm going to get there is I'm going to get a over negative x equals tangent of phi. So opposite over adjacent equals a tangent of that angle. Note that my x is negative because I'm on that side of the x equals 0. Okay. Now you might be saying, hey, this relates x to phi, but how do we talk about dx? And we do it by taking a derivative. So I have a over negative x equals tangent of phi. Rearranging that, I have x equals negative a over tan phi or negative a cotangent of phi. So far, so good on the algebra. Let's take a derivative of both sides. On one side, we have dx. Check. On another side, we're taking the derivative with respect to the angle because that's our variable. This is kind of like a u substitution. So we can take the negative a and put it in front. It's a constant, so it's not going to change. But here's the big question. What is the derivative of a cotangent? And I actually am super happy that no one knows this off the top of their head. It's not something you should really waste brain cells on. It is negative cosecant squared. Certainly not something I have memorized. Okay, negative cosecant squared, but then we're taking the derivative of the inside as well. So we have a d phi there. All right. This is beautiful. This looks great. Our minus signs nicely cancel out. We have something we can plug into our integral. So we're going to plug that in for the dx. I'm also going to combine these two signs, so we're going to have a sine cubed. Okay, so my b, mu naught I over 4 pi. I have a 1 over a squared right now. I have a sine cubed of phi, a cosecant squared of phi, a d phi, and notice I also have this a right there, and I'm just gonna put it right there if that's okay. Okay, a went outside, this one right there. Okay, this is starting to look really good. We're almost to the point where we can actually integrate this thing. Cosecant, that's 1 over sine. So I really have a sine cubed times a 1 over sine squared. One of those a's goes away. So a sine cubed over 1 over sine squared, that leaves me just a sine to the first power. And we can integrate this. This is a problem that we can now do. I do want to put in some limits before we integrate this. So notice that we've gone from integrating chunks of wire, so ds's, to integrating d phis. So I still need to integrate along this entire wire from x equals negative infinity to x equals positive infinity. So when x is negative infinity, what will my angle be? Will it be getting smaller or larger as we choose dx's further and further down the line? So that angle phi, that's right there. As I go from here to here to here, did it get larger or smaller? Got smaller. And as I go further and further away, it'll get closer and closer to 0 until I've reached negative infinity. And at that point, phi will equal 0. Okay, so that's where we're going to start. We're going to start at 0. And now let's go on the other side. So on the other side, I choose a ds. My angle is still between ds and r. And so now that is my angle phi. So as I get further and further down towards positive infinity, is that angle going to get larger or smaller? Larger. And what will it approach as x approaches infinity? 180. Perfect. 180. Okie dokie. All right. What's the integral of sine? Negative cosine. mu naught I over 4 pi a from 0 to 180 of negative cosine of phi. Plugging in my limits. I have negative cosine of 180 minus a negative cosine of 0. And what is the cosine of 180? Negative 1. And so that will become a positive 1. And what is the cosine of 0? Just positive 1. Which again becomes a positive 1. So really we have 1 plus 1 here, which is 2. So I have 2. Let me just like note this whole thing is 2. I have 2 mu naught I over 4 pi a. Of course, this will become just mu naught I over 2 pi a. Not over 2 pi a. Okay, and this is the B field. And in this particular case, it was in the positive Z direction, right? Okay, really quick, if I had chosen a spot on the bottom of the wire, so if I chosen this to be my spot, there's my ds, there's my r hat, well, r vector. Can you guys do me a really quick right-hand rule on ds cross r hat for this scenario? I like that, you got it. ds, r hat, thumbs into the board. So we start this way with our ds. We swing our hand around until my next finger can point in the downwardish direction. My thumb should be pointing into the board. Start with your pointer that way. Then get your next guide towards the floor. Use your right hand. Use your right. Yeah. Get it to point that way. Don't mirror. Yes. There we go. Yeah. No, the mirroring. Okay. We're into the board, right? The thumb's into the yeah. So this is going into the board. Negative Z hats, which again, if we do our curly finger thing, we point our thumb and curl our fingers around. On the top, it's coming out of the board. On the bottom, it's going into the board. All right, sounds good. Okay. Okay, so let me go ahead and circle this up. This is the magnetic field of a long straight wire. Some distance A away from the wire, where this is some perpendicular distance, I should say. Some perpendicular distance A. So instead of having our magnetic field depend on R, we're having it depend on the perpendicular distance between the wire and whatever point we want to talk about. Sound okay? I hope so. Okay. This was a gross derivation, right? Like the geometry there was a little bit beyond what's beyond the pale. It is because the geometry was weird. This whole long straight wire thing, it doesn't gel very well with magnetism, which is all about loops. And so having to transform something from a straight line into a loop can get rough sometimes. We're going to do one more of these, which will be very easy comparatively, and another really kind of nice equation to have where we're going to get the B field of a loop of wire. And so let's talk about this easy problem we're about to do. It's going to be a circular loop of wire. Circular. So if I have a circle with some sort of battery in it that's going to produce a current like this, I want to figure out the magnetic field in the center of that loop. And I'm going to tell you that this loop has a radius r. Sound okay? Okay. Let's do this the same way. We'll look at, we'll identify our DS's. We'll do a cross product. We'll look at our R and see what it looks like. So let's do this step by step. There's a DS. It's going that way. It goes in the same direction as the current. Since I'm looking at the point in the center of the circle, my R just goes from the DS, the chunk of wire, to the center of the circle. So let's go ahead and let's do this cross product first. So ds cross r hat, r vector now. So again, the r hat is just has a magnitude of 1. So I have the magnitude of ds, I have 1, and then I have the sign of the angle between them. What is the angle between my ds and my r vector? 90. Will that change if I choose a different ds? No, right? Every ds I choose will be along the circumference of this circle. And for every r, it's going to be radial. So I'm very comfortable just putting in a constant for that. Even though my DS's, I'm gonna move them around. Sine of 90? 1, perfect. Okay, so this integral, it's already starting off very nicely. Mu naught I over 4 pi ds over r squared. Okay, really quick, let's do the direction as well. If you do a ds cross r, what direction do you get? Great. I see some thumbs pointing towards the back of the room. So you have the ds, the r. As you go around that circle, does your thumb change direction? No. Okay. So all the DS's are going to add a magnetic field in the same direction. Sound good? Okay. Positive z, which again we'll come back to that once we do all the math. Okay. This looks really nice. So this r, this is really the radius of that circle, right? As I go around this circle, does that radius change? No. So we can just take that outside. Mu naught I over 4 pi, and I'll do a capital R squared. Okay, this is starting to look very nice. All we have to do is put some limits on that. So if I start here and go all the way around, let's say I start at ds equals 0. And if I go all the way around, what should I go to? What is it called when you go the entire length around a circle? Not the diameter, the circumference, right? So you go all the way around the circle, that's the circumference, that is 2 pi r. So we add up all our ds's until we hit 2 pi r. So, and you really can just like write down 2 pi r for the answer to this integral, but just so everyone's kind of happy, I integrate ds and I get s, and I plug in my limits, and now that's squared, and now I have 2 pi r. Does that make sense? And that r cancels out one of those r's, and we end up with a really reasonable mu naught I over two r. Okay, did all the cancellations go well? Algebra, happy? This, so this, let me label it. This is a circular loop, radius r. Okay. Few things. Note that was an easy integral to do. Magnetic fields like loops, they're much easier to do. Next, the direction here, we got that it came out of the page. If my current was the other direction, it would go into the page. And if you want that, I don't remember if I used this right hand rule last time. There's another right hand rule you can use where you take your right hand and you curl your fingers around in the direction of the current and point your thumb. And the direction your thumb is pointed will be the direction of the magnetic field at the center of that loop. Make sense? Out. If we're going the other way, it could be whoosh. Okay. Like everyone actually pretty happy? Okay. Okay, cool. This is great. So far, so good. Notice that we're going to have a couple different equations for magnetic fields. Do make sure that you are choosing the correct one for your situation. You can't just pick one off the sheet. You have to make sure you have the magnetic field for whichever situation you have. But if you're happy with that, let's do a few homework problems. I think I'm going to start with number 12. Okay, so number 12, we have two wires. We have a long straight wire carrying some current I2, and we have a loop of wire carrying some current I1 in the counterclockwise direction. This loop of wire has a radius r. And we are going to want to know where we would like the magnetic field at the center of the loop to equal to 0. Okay, and so we have two things making a magnetic field. We have the loop of wire and we have the long straight wire. And so the first thing we need to know is we need to know what direction to put the current of I2. So first off, looking at I1, at the center of the circle, what direction will it make a magnetic field in? Out of the page? Okay, so I got one out of the page. So that means that I2, whichever direction it's in, right there, it needs to be into the page. So should we set I2 to be going to the left or going to the right? Like that. So if I need my fingers to go into the page above the wire, I put my thumb to the right, to my right, your left. Okay. So we need I2 to go that way. Excellent, excellent. Next, since we want next thing, we want, interesting, we want the ratio of I1 to I2 so that B will equal 0. B total will equal 0. All right, so we need to figure out which one will be stronger and by how much, basically. All right, so I have the B of the loop going in the positive Z direction, plus the B of the straight wire going in the negative Z direction. Those need to add up to 0. And the big key to this problem is make sure you put in the right equation for the right geometry. Where my loop of wire, we'll put in mu naught I over 2R. Mu naught, that's I1 over 2R. And then for our long straight wire, we'll put in mu naught I over 2 pi A. But we need to figure out what to put in for A, where A is the perpendicular distance between the wire and the spot in question. So in particular, this distance. What would you call that? I would call it R2. Yes, R is a good answer. R. Okay, and this needs to add up to 0. This really needs to be a minus sign because it's in the negative Z direction. What can we cancel? Mu naught. Can divide everything by mu naught. What else can we cancel? 2 and R. Sound good? And we'll be left with I1 minus I2 over pi equals to 0. And since we wanted the ratio, so we want I1 over I2, let's arrange this so it's I1 over I2. So I move I2 over pi to one side, and then I divide both sides by I2 to get 1 over pi. Sound reasonable? Excellent. Okay. Okay. That makes sense? There are a whole bunch of directional problems in here. And I want to do 2 of them. I want to do number 11. And this is going to be sad because I need to draw a coil. Man, that's a terrible coil. Let me just. It was not, but thank you for saying that. Okay. Where the current on the top here is coming out of the page, And the current on the bottom here is going into the page. So it's going kind of, whoosh. Do I do that? It's coming out of the page, going into the page. So it goes like this, and then it comes like that. Can everyone kind of tell what direction that is? So yeah, on the top of the coil, it's going out, bottom it's coming in. So it's doing this. And the opposite coil, it's going to be doing the opposite thing, where the current's coming out of the page down here and it's coming into the page down here and out of the page down there. So it is going like this and then coming down. Make sense? Okay. So we're just gonna A, B, C. If I have my coordinate system X, Y, and Z, for A, if I want the B field in the center of that, in terms of X, Y, and Z, what direction will the magnetic field be? So out of the board in the positive Z, right? Okay, positive Z. And then for B, I want to know the magnetic field right through the center of that loop. So choose any one of the single loops and do a right-hand rule on any single loop. And so I like this. So you're putting your fingers out and then down. So it's that situation, but then they're just a bunch of coils lined up, right? Okay. So the magnetic field looks like that. The magnetic field is in the positive X direction. Excellent. How about C? Which way should the magnetic field be? Negative X. Excellent. Reverse the current, you'll get the opposite direction. Okay. Okay, that seemed to go pretty well. Let's do just one more of these, and I will be happy. I'll be confident in your ability to do the right-hand rule. Okay, so number 4, we have 4 identical wires carrying currents that are almost identical, except some of them are coming out of the page and some of them are going into the page, like this. And so this is, and they give us a compass here, north, east, south, and west. And we want to look at the spot right in the center of the square. And what we're asking now is each of these 4 wires, which are like strung in and out of the page here, and some of the currents are going this way and some of the currents are going that way. Each one of these wires is going to make a magnetic field at this point in the center. And if you add up all the magnetic fields, where are the total magnetic field be pointing? Everyone kind of get the question? So let's go around the circle. So for this guy in the northwest corner, which he's either going to make a current in the a magnetic field in the clockwise direction or the counterclockwise direction. Which way will it be? We're all going to point our thumbs. So it's going around like this, right? Yes. Where if you extrapolate that at the center of this square, its magnetic field will point that way. Sound okay? Okay, what about this guy in the southwest corner? Same or opposite? The same, good, because it's the current in the same direction, right? So you just move your hand down and it works. But that means in the center here, it will be going that direction. So right now, the overall magnetic field should be pointing straight north because the sideways are going to cross out. Okay, to continue going, that guy in the northeast corner, is it going to make a magnetic field clockwise or counterclockwise? Clockwise, I like it. So it's going to go around like that, right? So it will have a field that direction. Last one, clockwise or counterclockwise? Also clockwise. So its field would be that way. So if you add up all these fields, what direction will the total magnetic field be in? North. Because since these all had the same current, but just in different directions, they're all the same distance from the center. They all have the same magnitudes here. They just have different directions. So their sideways are going to cancel out. And their north, their east and west are going to cancel out, and their norths are going to add together. Okay. Does everyone feel really happy about the right-hand rule? Okay. Does everyone feel that the biot-savart law is really irritating? Yes, good, good. Okay. We're probably never going to use the biot-savart law again. It's not the most fun way to do things. Okay, so after this, let's do magnetic force between two wires, and then on Tuesday we'll do Ampere's law. Okay, B force between two current carrying wires. Okay, so the idea from the last chapter, we have the idea that if you put moving charge inside of a magnetic field, it will experience a force. From this chapter, we have the idea that moving charge just by itself will create a magnetic field. So if I have two wires that are close enough together that they will be in each other's magnetic field, they should exert a force on each other. Okay, so I have these two wires. I'm not going to specify whether their currents are identical or not, but they're both going to be in the same direction. I'm going to call it top and bottom. I'm going to call this the X, the Y, and the Z direction. So what am I going to do first? First, let's map out what sort of magnetic field we expect to see from the top wire. Okay, so on the top side of the top wire, which way will the magnetic field be pointing? Out of the board, okay. How about on the bottom side? Into the board. Okay. And if I tell you that these wires are some distance d apart, could you tell me what the magnetic field from the top wire at d at the bottom wire will be equal to? Or really, should I ask, should I be using the equation for a magnetic field from a loop of wire or a long straight wire? Long straight wire, which was mu naught I over 2 pi a. But instead of a, what I'm going to put in here? I'm hoping you guys are going to tell me d, because that's the distance from the top to the bottom wire, right? So at the bottom wire should be in a field of mu naught I top over 2 pi d. That's going into the page. Okay. Next, we know that a magnetic force of a wire is the current times L cross B. Okay, so I'm going to look at the force exerted on the bottom wire here, where L, oh, I don't want to do that. Wow, they changed that. That's not helping me. Sorry, where the current's going that way, so like L would be going the same direction of the current. The magnetic field in this case, so this is L of the bottom wire. This is the current of the bottom wire. And this is the magnetic field of the top wire. Does that make sense? So which way will the force on the bottom wire be? No, you had it. L, B. Oh, yeah, so force towards the top of the page? Excellent. So we have a force, top on bottom, going up. And we could even write down an equation for this. Force of top on bottom. What is it? I L cross B. Okay, this was I bottom, L bottom, and B top. Where you guys just did the right hand rule for me. And you got y hat. We could add a sign of the angle between the current and the magnetic field, but I'm hoping that you guys would see it would be 90. And sine of 90 is just 1. So it'd be fine. And then we could plug in that equation right there. So I have mu naught I top over 2 pi d. And the only thing kind of left to look at is this L. where L, that's just the length of wire that we're talking about. Now, a lot of times when you're doing this, you talk about this force in terms of unit length. So you just designate some unit length, like L. And so you say the force per unit length L equals mu naught I bottom I top over 2 pi d, where you just took this length and you divided both sides. Okay. Okay, does this make sense so far? Let's really quick just go through it the opposite direction. So if instead of the magnetic field of the top at the bottom wire, I wanted the magnetic field of the bottom wire at the top, what would be different about this equation? The direction would change. Okay, so let's do that. So if for the bottom wire, my current's going in the X direction, I'd have magnetic field coming out on top, and on the bottom would go in. Okay. So instead of out of the board, into the board, it'd be out of the board. There's only one other thing that would change. What is that? It would be I bottom instead of I top. Okay. Then say again? Yeah. So let's look at that next. If we wanted the bottom on top here, this would be top, this would be top, and this would be bottom. Good. Okay. And in that case, this cross product, you'd have L in the same direction, but now the magnetic field's coming out of the board. And so instead of up, you get down. So you get a force bottom on top, like that. Okay. And so yeah, so you'd have top, bottom. This would be top, this would be top, this would be bottom. Okay, would the length matter whether we use the top or the bottom wire? No, right? We'd still have like whatever unit length, we'd use our unit length. So that would be the same. Instead of I bottom times I top, we'd have I top times I bottom, but that doesn't matter. The distance between the two wouldn't matter either. So this would be the exact same thing. The only thing that would really change is this direction, where you notice we could more succinctly put the direction as saying, if the currents are in the same direction, these wires will pull towards each other. Does that make sense? Towards each other. And that should kind of make sense to you if you start thinking about these wires as magnets, where they have a north side and a south side. And if their magnetic fields are lining up, north, south, they'll want to come together, right? As opposed to a situation where you had two wires, but the currents went in opposite directions. Now the magnitude of that force they'd experience would be the same, but the directions would be different. So if I look at the top wire in this case, I put it in the same direction, so its magnetic field will be in the same direction. But then when you cross this magnetic field, it'll cross the top, bottom, bottom. Now the L is in that direction. That's going into the page. So now we have L into the page and the force going down. So here the force will go down. Force of top on bottom. And if you go the opposite direction, you'll find this force will go up. Force bottom on top. Which you're trying to put two north sides of the magnets together. They don't want to go together, so they'll push apart. So these currents, it really is beneficial to think about them as magnets, because they'll come together if you line them up. They'll push apart when you unalign them. They make the magnetic fields just like they would otherwise. Okay, I'm close to wrapping this up for the day because I don't want to start Ampere's law until I have a long time to talk about it. But let me ask you this question, because this is my favorite question. I have a spring. Which is made up of a whole bunch of parallel loops like this. And I'm going to hook it up to a battery so that current's going through here, not like that, but I guess it really doesn't matter. But like this, currents like so. When I turn the battery on and current starts to flow, is the spring going to compress? Is it going to expand? Or is it not going to change? What do y'all think? So I turn on the currents. I can even put a little switch in here. I turn on the currents. What's going to happen to the spring? Say again? Good thought. Okay, so but why do you choose expand instead of compress?
I don't know. I was just kind of thinking, well, I don't know. It's probably nothing to do with it, but you know, how he can like expand some stuff.
Oh, okay. That's actually kind of interesting. Let me say that the magnetic force is going to be larger than the thermal consideration. And there is going to be a magnetic force here. Because we have these loops of wire that all act like magnets. Are they all going to line up and want to come together? Or are they all going to be like north to north and want to go apart? What do you think? Let me ask you a right-hand rule question. For this top loop at the top here, the current's going around like this. I see lots of magnetic fields going up. How about the next loop? Up. Up. So are these magnetic fields lining up together? Right. This thing is going to compress. Because it is a bunch of magnets and you've lined them all up. So it's like, okay, I want to come together. Just like this wire up here. These two wires, they had currents going the same direction. They wanted to come together. And this is actually very interesting because this is a way that you can store mechanical potential energy via electricity. because as you compress that wire, that's storing potential energy in the spring, right? So you've stored energy in that spring via this electricity. Sound good? Okay, let's wrap it up for the day. Ampere's law on Tuesday. Chapter 11 homework due tomorrow. Online people, are you okay? I haven't even turned the chat on. That's probably really bad. Sorry. Yeah, they would have yelled. But you guys okay? All right, I will trust that you are. See you Tuesday then.